Good morning, ladies and gentlemen. Let's talk a little bit more about energy.
Energy!
Something I wish I had more of right now. I'm dying a little bit. Okay. All right, so work changes energy. Review our work energy theorem. Work is force times distance. Work changes energy.
Yep. You got words on the top, equation on the bottom, say the same thing.
Let's play. We are going to go to the cart, the pass cart, and we are going to push in the plunger, release the plunger to make the cart go. I guess I can use this. Okay, so let's go 1, 2 detents right there, and boink.
Sweet.
Okay, so what question do I have with this? My question is, I'm gonna do it again. Describe the chain of work and energy transformations that occur.
It was a simple thing, but there's 4 things go on. It's this, that,
This, and
this, that, this, and that.
There's 4 things I want you to be thinking about. 4 transformations between work and energy.
Do that again.
So we'll go 1 and 2 right
Okay.
there. Okay, and boink, and boink. Whoosh. Okay, and I want you guys to be thinking about this from the very get-go, starting now. I love it when it hits that side because it's not even it.
Wait, let it do it again.
Let's go all the way.
It's fun.
Okay, and wait. Oh, what happened that time?
A crash.
Okay,
All right.
so pause the video. This, that. Write the 4 things.
The chain of work and energy transformations that occurred.
Okay. Wink. Statement. Important. Anytime a force is exerted through a displacement, energy changes. A force through displacement. Didn't we do that over there?
You exerted a force with your finger,
Yeah, on the, what do you call it, the detent?
the plunger.
The plunger. Oh, it's the plunger. The
Plunger has detents in it.
plunger has detents, like detention. Okay. Work done compressing the spring.
So that was the
is
first thing.
Oh yeah, okay. So the first thing, work done compressing the spring is stored as potential energy. And can you see it from this side okay?
Yeah.
Right? I'm exerting a force and it's moving a displacement.
Can you see the spring on the inside there on the, right there?
I'm like,
Here, do that again.
okay, right?
See, there's a spring.
1, 2,
She's
3.
doing work, compressing the spring.
yeah. And so that is the first part of that's the first leg in the
That's
chain.
the this,
Yeah, that's the this, okay? So
And
work
it's-
done compressing it.
and
stored
there's the
as-
that.
And oh, sorry, this is the this. Work done is done compressing the spring.
Those things are
Hey.
built like nails.
How did that even happen?
So there's work done, and
Okay.
that produces potential energy in the spring.
Stored in the potential, stored as potential energy. Okay, that's the first 2. And here is our equation for potential energy. Energy stored in a spring is represented by this equation. We will use this later to do stuff. Okay, this is my 3rd thing that you should have written down. The energy released by the spring does work on the cart.
When you push the button. Yep.
Okay, when you push the button up, beep, beep, beep. That button. And last but not least, well actually, yeah, that's the next one. Okay, stay there. The work done on the cart makes it move, giving it kinetic energy.
That's right.
So those are the 4 things, that's this, that, this, and then that.
Work energy, work energy.
Okay, so we've seen this relationship
Here's a
before.
reminder, yeah.
Yeah, so work is the change in kinetic energy. Work changes energy, in this case kinetic energy. And we know that in order to find kinetic energy, in order to find the change in anything, we do final minus initial. The change in kinetic energy also, how many times can I say kinetic energy? Is also equal to 1/2 mv in the delta v squared.
Yep.
Okay, so, oh, this is kind of cool.
Here's the this, that, this, that.
This is the this, that, right? And you can see here that we have the work done on the spring results in energy stored in the spring, and the spring does work on the cart, and that in turn is transformed into kinetic energy.
And it goes down the track.
Yeah. But so not only is this our this, that, but this is the relationship between variables.
And there's equal signs between them. What does an equal sign mean?
The same thing as.
Yeah.
Okay, so using this, that, answer this question. How could knowing the speed of the pass car after releasing the plunger help us find K?
What? ¿Qué?
¿Qué?
¿Por qué?
Okay? And the K we're talking, oh, wrong way. This one right there. How can we find this? Can we find it? How do we do this? Okay.
And the answer is right, back one more.
Right here.
It is right here.
It's somewhere in here, hidden in plain sight. Okay, let's give him some data. Pass car.
All right, I'm gonna stop this because I gotta set this up.
Oh yeah, okay. All right, we are going to play with the PhotoGate with the LabQuest. LabQuest over here, PhotoGate here. And this is our pass car. And what we are going to get from this setup here is the velocity of our cart. So what I'm gonna do is I am going to
Do a little work.
dink 2 detents in on the plunger, and I am going to hit it, and Boykin is going to.
So I'll say go and then you hit it, all right?
I'm ready when you are.
Go.
Sweet. Okay, and what did you get for our velocity?
0.796 meters per second.
0.796 meters per second.
And the mass of the cart is 0.250 kilograms.
250 kilograms. Okay, ladies and gentlemen, have some that looks like. Did you flip it for them?
Yeah, I flipped it, so.
Okay. Now let's go back to our question. It's not up there, but it's how could knowing the speed of the pass car after releasing the plunger help us find K? Okay, let's go up to the board here.
All right.
So we found out the velocity.
We
while
can
the car was
get
moving.
we can get the kinetic energy, and that K that we're asking for is a spring constant, but we need the kinetic energy in order to get it.
Yeah, so we can use these relationships here to help us out. So let's start with, like you said, K, which is 1/2 mv squared, change in
Yeah.
velocity.
The original kinetic energy was 0, so.
Yeah, so that minus 0 gives us the number we want. So 1/2, the mass of the car was
0.250 kilograms.
250 kilograms times the velocity. The change of the velocity was 0.796 meters per second. Let's get our answer here for our kinetic energy. Thank you. So 0.5 times 0.250 times 0.796, and I get 0.0. We'll call it 0.0. Let's just keep it all. 0.0995.
Joules.
Joules.
Okay, so
So
now we've got the kinetic energy.
we've got this. Oh, yeah, we want that.
So we want to solve for this guy.
So right now we have this. We want to solve for something that's here, and we know that these two things are equal.
Yep.
So let's go ahead and just say the potential energy stored in the spring.
While she's doing that, boys and girls, how would you solve this for K? Go ahead.
Do it.
Do it. So the first assumption we're going to make is that that kinetic energy is equal to the potential energy stored in the spring
This part right here.
because of the work energy theorem.
And then once we have our equation written out, this is little k. Okay, we're trying to find that spring constant. So this is the equation we want to use.
Something's missing. There's something that we don't have.
We don't have, what does that x stand for again? Delta x, baby. Okay, and actually I need that, oh, there it is. I'm like, where'd it go? Okay, so we want to measure the change.
That's the displacement of the spring.
Okay, so I'm gonna go ahead and put this on here as best I can. And that looks like, let's call it 4.65.
4.65.
Write that down.
That's x original. And now it's shorter.
We're gonna
What do you want to call that?
1.90.
1.90. So
Okay, so it's 4.69. 4.69 centimeters
that's the
minus
final minus the original, which was
1.90 centimeters.
9 minus 0 is 9. 16 minus 9 is 7. Boom!
2.79
The human calculator.
So, oh yeah, no, that's good. Okay. So
Now,
what
first
do
of
we do
all,
with that?
we're going to have to change that to meters by moving the decimal
yeah, you're
3
right.
places to the left.
2 places, right?
Yes.
So we've got 0.0279 meters. So let's go and plug some stuff in here. We now have our displacement down here. 0.0279 meters squared. Don't forget squared. Divided by 2 times. What do we put for this? This equals this. So we get to use this number. Okay, let's do it. So 2, oh, wrong. We're gonna go 2 times 0.0995 divided by 0.0279 squared.
Should get a big number.
Yeah, 250, we'll call it 256.
256, and the units are going to be newtons per meter.
Per meter.
So that means that if you compress that spring in there 1 meter, which you can't do, it would require 256 newtons.
Use your imagination.
That's right.
Okay, all right. So that is our explanation of how to do this, the relationship between the work energy theorem, and now work, Miss Moore. Ooh, work. Page 276, numbers 25 and 26.
And this is in the AP Physics textbook.
AP Physics textbook.
That's right, y'all.
All right.